Alright, so welcome to another video on polar coordinates. In this video what we're going to do is we're going to be looking at this particular problem here where we have a semicircle that goes from the top of the y-axis to the bottom of the y-axis. So it covers the second and third quadrant on our xy plane. And basically we're told to integrate the following function, so it's just going to be the square root of this particular expression here, which is in itself fairly complicated to integrate using Cartesian coordinates. So what we'll do is we will transform this into polar coordinates using the same method we learned in the last video, and hopefully that should simplify things a lot for us. So the first thing you need to notice is obviously for polar coordinates we're going to have the following parameterization, so r cos theta, then y is going to be equal to r sine theta, and we also have the relationship x squared plus y squared equals to r squared. And now what we're going to do is we're going to establish the new limits of this region of integration D. So in order to do that, what we're going to do is we're going to look at how theta and r are behaving in this case. So remember, theta is just the angle from the x-axis on this side, on the first quadrant. And basically we're just going to count what quadrants or what angle of that rotation does theta actually cover. And in here we can see that it goes from the top of y-axis, so it will be pi on 2. So it starts from pi on 2, and then it basically finishes at 3 pi on 2, which is about 270 degrees. So that's going to be the boundaries of integration for theta. And then the limits for r are going to be the following. So where does r go here? So r goes from 0, so that's the minimum value of the radius, and it goes to this constant value of radius 1. So basically our limits for r are going to be from 0 to 1. So that's how we define those. And now what we're going to do is we're going to make the substitution in here. So just rewrite the integral as going from pi on 2 to 3 pi on 2 and 0 to 1. So now we're going to have the following. We're going to have 1 minus r squared, because remember that x plus y squared is going to be r squared, so that's going to be this. And then dx dy is going to become r dr d theta, and it's very important not to forget the r there. So now we're going to get the following: pi on 2, 3 pi on 2, then from 0 to 1 of r times square root of 1 minus r squared dr d theta. And now in order to integrate this, remember that we can use substitution here if we make some variable u equal to 1 minus r squared. And then we're going to have du equals to minus 2r dr. Because we have the r dr elements here, the only thing we're missing is the minus 2. So in order to put a minus 2 here, we need to put a minus half on the other side, so minus 2, 1 over minus 2 on the outside, just to balance it out. So then in the end, this integral is going to become the following. We're going to get minus 1 on 2 from pi on 2 to 3 pi on 2 from 0 to 1 of the square root of u du d theta, which is equal to minus 1 on 2 pi on 2 3 pi on 2 of 2 on 3. And I'm going to substitute back for u, so this is going to be 1 minus r squared to the power of 3 on 2. Now we're going to have from 1 to 0. So then this is going to become the following. Oh, don't forget the d theta here. So now we're going to have, so we can take this out, so basically this cancels out with this, and then the 3 comes out, so that's minus 1 on 3 from pi on 2 to 3 pi on 2. And then this element here, once we substitute for the limits of integration, is going to give us the following, so that's going to be minus 1. And then from here onwards, what we can do is we can integrate with respect to theta, so that's going to be fairly simple. This is going to cancel out with that. So in the end we have all 3 theta 3 pi on 2 pi on 2, and this is going to be equal to 1 3 times 3 pi on 2 minus pi on 2 equals to pi on 3. So that's going to be our final answer. So we just saw that basically transforming the coordinate system here to perform this integration, we just found the answer to this integral by simply performing this coordinate change. And polar coordinates come in handy in a lot of cases, and they can be applied to a lot of different situations that involve some sort of circular kind of region. It doesn't have to be a circle necessarily. It can be anything that can be described in terms of a polar graph, and that's something that I'm going to discuss in a later video. But essentially, for any simple region, we expect to have a simple enough integral that we can perform using our standard methods of integration. And in the next video, we're going to extend this by solving some more examples using polar coordinates.